Welcome to the presentation on acids and bases. This presentation will cover chapter 14, and this will, I believe, only be a two-part presentation because I believe the material can be covered in a relatively short order. So let's move on. We will not be doing a student learning map. You can certainly pause and take a look over this. I do like the unit essential question, so it most likely will be on the chapter 14-15 combined test. Otherwise, I will move on. And likewise with the section 1 and 2 together, this lesson question as well. Good question, but we're moving on. Okay, in 14.1, here are your objectives. I don't see a star beside any of these objectives, and so they come right out of your book. Understanding 5 general properties of aqueous acids and bases, meaning dissolved in water. You should already know the nomenclature of binary and ternary acids. You should know the nomenclature of bases. You should be able to, after reading the chapter, list 5 common acids used in industry. And you should be able to define terms of acid and base according to a leading theorist named Arrhenius, and also understand and explain the difference between strong and weak acids and strong and weak bases. Okay, let's compare really quickly. Just sour milk, the reason why it's sour is because it has a buildup of lactic acid in it. The tart flavor in soda pop is normally, not always, due to phosphoric acid. Of course, citrus fruits have citric acid. Apples have malic acid. Grape juice, have tartaric acid. Stomach acid is called hydrochloric acid, and battery acid is sulfuric acid. On the base side, ammonia is actually a solution of ammonium hydroxide. Lye soap or lye-based oven cleaners have sodium hydroxide in them and are very dangerous, like many of the acids are. Milk of magnesia, which is a laxative, is magnesium hydroxide. And acids can either have aluminum hydroxide or sodium hydrogen carbonate, which is also called sodium bicarbonate. So acids, generally, acids would have these properties. So generally they will have a sour taste to them. And of course you don't really want to taste an acid, but many foods have acids in them and they're generally going to have a sour taste. Acids will change the colors of natural, organic, and synthetic indicators, which are designed to color change in the presence of either an acid or a base. Some acids react with active metals to release hydrogen gas, and so when you see acid bubbling on a metal, and the bubbles are probably hydrogen gas and they are explosive because hydrogen gas is highly flammable. Acids react with bases to form salt and water when they neutralize, so an acid can neutralize a base and vice versa, and the product is always a chemical salt and water for traditional acids and bases. Some acids can conduct electricity, so they're considered electrolytes. Remember those that would ionize. Nomenclatures, you should be able to name and write formulas for binary and ternary acids, and you could go back and review your Chapter 7 material or certainly contact me with questions. I'm going to skip over this. There are 5 slides on 5 common acids that are mentioned in your book on industrial level acids. You can read over this on your own. Sulfuric, nitric acid, phosphoric acid, hydrochloric acid, and acetic acid. And you can read over all of those, go back and pause and take notes on any of the slides. Some questions could be asked about some of the main characteristics of those acids. Bases. So we had some properties of acids. What about bases? Well, bases generally will taste bitter. If you've ever had the taste of soap in your mouth, for instance, either on purpose, like me cursing in front of my parents, certainly earned literally having my mouth washed out with soap several times. I was slow to learn. But yeah, bitter taste. They also change the color of indicators, but they change the indicators different colors than acids. And if you have a template to look at, you can tell exactly what is what. Bases often feel slippery like soap. If it's safe to touch, it's going to be slippery. They will react with acids to, again, neutralize each other and produce salt and water, and bases are electrolytes. So there are three theories this chapter brings out on what is it to be an acid, what is it to be a base, chemically speaking. And Svante Arrhenius was one who characterized acids and bases. His theory, sometimes simply called the traditional theory without reference to Arrhenius, is probably a common theory that we follow, and it's one we've talked about and never really mentioned. But it is a very strict definition of what an acid and a base is. So not very many chemicals actually qualify as acids or bases under Arrhenius. There is a better theory out there, and we'll talk about that in section 2. But that's the Bronsted-Lowry. But okay, Arrhenius. What is an Arrhenius acid, AA? So right up here. So what an Arrhenius acid? It is any substance that will increase the concentration of hydrogen ions in solution. So if any chemical can put hydrogen ions in solution and make that concentration go up, Arrhenius would say, aha, that is an acid. An Arrhenius base, on the other hand, which is a very strict definition, is any one particular substance, any particular substance that can increase the hydroxide ion concentration. So therefore, almost all Arrhenius bases must have hydroxide in them, and very few substances would have the ability to produce hydroxides in solution to increase that concentration without actually physically looking like they have hydroxide. Now think about this. What is a hydrogen ion? I think I have my pen activated. Well, think about a hydrogen atom. If you have just a proton, right? So if you just have a proton and you have an electron that orbits and you remove the electron, what do you have left? You have a proton. So a hydrogen ion literally is just a proton. I find that amazing. Even though it's very simple, I still find that amazing. So what must all bases, according to Arrhenius, have? They must have hydroxide, or in some rare cases, the ability to form those hydroxide ions. So, strong acids and ionization. Remember from chapter 13 in our ionization equations. Here is one for the ionization of nitric acid. These acids are covalently bonded together. However, the bond is tenuous, and water has the ability to separate the covalent bond, to break that bond, and to separate them up and produce ions. Now, when water does this, and we see the equation up here, I have the pen activated so I can write on this. So notice that we're going to see hydronium ions forming. So that's really where the hydrogen ion goes. The hydrogen is not stable, so it bonds with water to form H3O, and then here's our negative anion. Strong acids, like nitric, will do this 100% or nearly 100%. So almost all of the products are right there. Very little, if any, would be over here in the molecular form. So therefore, they are electrolytes because they will conduct electricity very easily. The strong acids will all do this, to include hydrochloric, hydrobromic, hydroiodic, the halogen acids, right? Sulfuric acid, which actually undergoes a stepwise ionization. It loses one hydrogen at a time. So the first step would be to form H3O and a hydrogen sulfate -1 ion, both aqueous. And then this can actually, under more strict circumstances, lose the final hydrogen to make another hydronium, and finally the sulfate polyatomic ion. You get a lot of this in solution. You don't get as much of this because once it loses the first hydrogen, it's much more difficult to lose that second hydrogen. So, sulfuric. So, it's, like I said, it's a stepwise. And the hydrogen sulfate is a very weak acid. So it just doesn't ionize as easily. Perchloric is HClO4, chloric is HClO3, nitric is up above, and fluorosulfuric acid and carburenes are like what they sometimes call superacids, which we're not going to get into the discussions of superacids. We're just going to stick with traditional acids. This is a nice list to memorize because if you know the strong acids, then you know automatically if it's not a strong acid, it must be a weak acid if it qualifies at all. Okay, so weak acids do not ionize and undergo 100% ionization. They're always less than that. So WA weak acid undergo less than 100% and are weak electrolytes. The bond between the hydrogen and the ion it is bonded to is strong. And so therefore water does not have a strong ability to, an easy ability to actually break that bond. It can in some cases, but not a lot. These arrows should be up a little bit higher. There's a formatting issue. But what we see here is we see the reversible reaction. And when you see that reversible reaction, that simply means that your products can re-react to make the reactants again. And then the reactants would make the products. This will eventually reach equilibrium as both sides react at the same rate to create each other. And weak acids do this, and so you're going to have a lot of the molecules existing and very little of the ions existing to conduct electricity. So what would that be? Well, that would be acetic acid, carbonic acid, the hydrogen carbonate ion. Hydrocyanic acid, hydrofluoric acid. Now hydrofluoric acid, you think, well, HCl, HCl, HBr, and HI were all very strong acids. Why not hydrogen fluoride? Well, that bond is incredibly strong. Whereas these bonds can be broken by water, this one, very little can be broken by water. So hydrofluoric is actually a weak acid. Hydrosulfuric is actually H2S. And phosphoric is H3PO4. All of these are weak acids, and therefore they are weak electrolyte. Polyprotic acids. Polyprotic simply means that there is more than one hydrogen that can ionize in solution to form hydronium. Sulfuric, phosphoric are examples. Sulfuric is, let's see, I think the pen's still activated. Yes, here it is. So H2SO4, it has two hydrogens that it can ionize, and phosphoric, shown below actually, is H3PO4, and it has three hydrogens that can ionize. Whenever there is more than one hydrogen to ionize, that they will always ionize stepwise, one at a time, regardless of how quickly it occurs, that it's always one at a time. So here we have simply hydrogen phosphate as a gas, and we're just going to call it hydrogen phosphate. We're going to bubble it through water. When we do, water will be able to dissolve and then break up some of the hydrogen phosphates. When it does so, it will form a dihydrogen phosphate, polyatomic ion with a -1 charge, and hydronium, of course. Well, this dihydrogen phosphate, while it can re-react with the water, with the hydronium to reform the reactants again, because it's a reversible reaction and it's weak, that it can actually undergo an additional ionization. So I'm just going to take this and I'm going to put it on the second line down here. So this is the same substance. And if this collides with the water and with enough of an energied collision, if you will, to ionize it further, it can actually create then the monohydrogen phosphate polyatomic ion, 2 negative charge, and again an additional hydronium. Now, every time this happens, this is probably the easiest reaction water has. This is harder because the phosphate has a strong hold on both of those hydrogens. This is the hardest yet, because water, to pull that remaining hydrogen off, is incredibly difficult because that bond is very strong. It can happen, but it does not happen quite very much at all. So finally, though, if this were to ionize completely, then you would have your monohydrogen phosphate reacting with water in a very energetic collision. If that did occur, we could actually maybe see the phosphate polyatomic ion completely isolated and solvated, surrounded by water, and an additional hydronium ion. Notice on this side they're all aqueous, on this side they're not all aqueous, and they're all reversible reactions, indicating that they are weak. We have dealt a little bit with organic acids, and organic acids, to be an acid, must contain a carboxyl group. So that grouping right there in organic chemistry is what we call a carboxyl group. It's a carbon double bonded with the oxygen and then a single bond with an oxygen-hydrogen combination. It almost looks like it should be basic because that looks like a hydroxide, but it's truly not a hydroxide. It's the hydrogen that is weakly held and can ionize. Now they're weak, so that hydrogen still is pretty firmly bound, but water can pull some of those hydrogens off. This happens to be, of course, well, maybe you don't know, but this one happens to be acetic acid. That's the structural formula, or yeah, actually the structural formula for acetic acid. Okay, what about strong bases? Well, strong bases will, like strong acids, completely dissociate. We changed the word to dissociate because the bases are already ionic, and so there is no ions forming. The ions are simply being separated from each other, so we call it a dissociation. Notice in all of these, let's see what we have. I think my pen is here. Yep. So here we have, all the way down to here, these are our group 1 metals. So here are your alkaline metals. And then here is a small subset of the group 2 alkaline earth metals. So these, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So these 8 make up your strong bases, and they will dissociate 100%, and therefore they are also strong electrolytes. Weak bases, just like weak acids, do not completely dissociate, and so here I have ammonia bubbling through water. Water can actually combine with ammonia to make the ammonium polyatomic ion and a hydroxide. Because there is creation of hydroxides, it's actually functioning as a base. It's reversible, and most of your substance stays molecular in that form, and you get very little of this, but you do have some, and so it's a weak. So ammonia will do this, aniline will do this. Generally, bases are not very soluble, so their solutions are not very alkaline and are considered weak bases. Very few ions present, but we do have some strong ones. Safety. This is just a general safety, not necessarily I want to throw it on a test, but think about this. If you have a beaker, and that's a horrible drawing of a beaker, and you're going to add acid or water to an acid or water, what do you want to do? Well, you would always add acid to water. The reason for that is because if anything splashes out, it wants to be whatever was in the beaker to begin with. That wants to be the safer substance. So if you throw acid in this thing, even gently pour it. If it spits out, drops spit out, you want it to be the water. And so general safety tip. This is the dilution equation. We've already talked about how to dilute things where we have concentrated and dilute. But acids, more so even than bases in a lot of labs, are ordered in stock solution form, meaning they are very concentrated. So sulfuric acid you might find in like 18 molar, hydrochloric acid typically 12 molar, nitric acid might be 14 molar. I could be wrong on that one. But you buy them in concentrated form, and then you just dilute them down as necessary. So you pour a little out of your stock concentrated solution, and then you'll simply add enough water to it to achieve the desired concentration that you want. So anyway, here's just an example, but we've talked about dilutions before. All right, we're pretty close here, so let's just move on and get this section out of the way. So in this particular section, it's on 14-2, and it's on looking at 2 additional leading acid-base theories. One is co-credited between Johann Bronsted and Thomas Lowry, so Bronsted-Lowry. And the other one is credited to Gilbert Lewis, who actually created the Lewis dot diagrams and the Lewis structures. Now, naturally, he was very focused on electrons for those diagramming systems, and his method of identifying acid and base is focused on electrons. Okay, so let's take a look quickly at Bronsted-Lowry acids. Danish chemistry, J.N. Brønsted, and English chemist T.M. Lowry actually independently expanded upon Arrhenius and hit upon the same theory at about the same time, so they are actually co-credited with its discovery, even though they didn't work together. So in this case, what they do is, instead of looking at an acid as something that's going to create hydrogen ions, they're actually looking at what it's really doing. And what Bronsted acids are doing, and even Lewis acids, or Arrhenius acids, they are actually donating protons. So it's still, it's kind of the same theory, but it's really more a function of actually what's happening. So they're really proton donors. So any chemical that can donate a proton is considered a Bronsted-Lowry acid. All of these down here are Bronsted-Lowry acids. Here I have HCl. Hydrogen chloride is a gas bubbling through water. And notice what has happened. I have a chloride ion here, so therefore it's the hydrogen chloride that donated the hydrogen ion. And where did it go? It went to the water to form hydronium. So this was the donor, that's the proton donor. Water is the proton acceptor, and this qualifies then as HCl being a Bronsted-Lowry acid. Down here I have hydrogen chloride gas again, but now I'm bubbling through liquid ammonia. Well, what happened? If I look across here, I see a chloride ion without a hydrogen, so therefore the hydrogen chloride is again the hydrogen donor. And what happened? It went to the ammonia, which is the proton acceptor. And that's where the ammonium came from. And notice this is kind of cool notation here. Aqueous, right? Dissolved in something. But now we're showing a different solvent. So aqueous in an ammonia solvent. So just neat notation. Now down here, let's check this out quickly. Here I have water combining with ammonia. Okay, well, what happened? Let's look across, and I see a hydroxide without a hydrogen. So when I look back at the beginning, here it's the water that donates the proton, and it's the ammonia that is the proton acceptor. Well, water is now functioning as an acid. Unusual, right? Excuse me. And that's the same water we're drinking, you know, as long as it's not mixed with ammonia, of course. But water has this ability, depending on what you put it with, to do different things. Pretty universal in some cases, so amazing. Okay, what about a Bronsted-Lowry base, sometimes just called a Bronsted base? Well, a Bronsted base is simply any substance that can accept that proton. We just saw 3 examples. If a proton is donated, something accepted it. And that's all this is talking about. Whatever accepts that proton, we say, oh, that is the Bronsted base. And this is where it does split from Arrhenius, because Arrhenius was talking about hydroxides, and Bronsted-Lowry are simply saying it's accepting the proton. So it has nothing to do with hydroxides, and it's all about that proton. So Arrhenius bases, hydroxide ions produced in solution are Bronsted bases because they accept the proton. Bronsted-Lowry acid base down here, so right there. Bronsted-Lowry acid-base reactions are where the acids donate protons and the bases accept the protons. Okay, so donate and accept. Here again with polyprotic acids. Polyprotic, the word poly, of course, meaning many, so many protons. Anything that is monoprotic has one hydrogen to donate, and that would be like HCl, one hydrogen. Diprotic would be like sulfuric acid, where there are 2 to donate. Whether it will donate them or not is one thing, but it has 2 to donate. This would be like 1 proton. A triprotic would be something that would donate 3, and I know of only 2 substances right off the bat. There are more, but H3PO4 and H3PO3, the phosphite version. So then in general, we just call di and triprotic, we just call them polyprotic. Remember that in a polyprotic acid, each proton is donated separately, stepwise, and always the first step will result in the highest concentration of product. So because that first step is easiest for water to separate one hydrogen ion from the phosphate. And so it's not terribly easy for water, but it's the easiest step that water will experience. After that, it becomes much more difficult to do the second or the third step for water, just because of the strength of the remaining bonds. All polyprotic acids will have a solution that will contain a mixture of all of everything you see here, with the first step always being the highest concentration and then less and less. So there'd be very, very little phosphate actually just by itself solvated in solution. Okay, we are 2 away from being done here, so thank you for sticking with me. Gilbert Lewis, did a lot of work with electrons, very much focused on electrons. He also generated a theory of acids and bases, but his was very much about electrons and what electrons are doing. So he has the broadest definition that we'll talk about. And basically what he said is an atom, an ion, or a molecule that can accept an electron pair to form a covalent bond is a Lewis acid. So this sounds opposite of what Bronsted-Lowry said. But remember, Bronsted-Lowry, we're talking about hydrogens being accepted to be an acid, right? And this is a Lewis acid, and he's talking about accepting an electron pair. So actually I said that wrong up there. I am sorry. Got it. Crisscrossed. A Bronsted-Lowry acid is a proton donor. And now we're talking about accepting, but what are we accepting? An electron pair. So it's not about protons at all, it's about accepting an electron pair. How can this happen? Well, imagine, if you will, we have a hydrogen ion. That hydrogen ion, being aqueous, reacts with ammonia. When it does, ammonia has an unshared pair of electrons. When that unshared pair of electrons around ammonia is involved in a collision with this hydrogen ion, the hydrogen ion is immediately attracted to those unshared pairs of electrons. When this happens, what results? We get the ammonium polyatomic ion. And it's because of that unshared pair of electrons from nitrogen which allowed that bond to be created. And when that bond was created, we have a Lewis acid-base situation. Who accepted the electron pair? The hydrogen. So that's why we're calling it the Lewis acid. So it's still an acid, but for a different reason. And then the Lewis base is whoever had the electrons to donate into the bond, and that would be, of course, the Lewis base, and that's the ammonia in this case. Down here we have a situation where I have a silver ion, and it's going to react again with ammonia. The silver ion is attracted to these unshared pair of electrons, so it accepts the electrons. It's a Lewis acid. The ammonia has the electrons to donate. Now, donate doesn't give them away. Donate simply means it'll allow them to be involved in a bond, and that is then called a Lewis base. The resulting complex, we now call this thing a complex, has an ammonia with 2 silvers, and we could also write it this way as well. I would encourage you to read the chapter and try some of the section review problems. I will be posting a little bit of ungraded work and a little bit of graded work on chapter 14 because I know time is short and we have other things to get to. So thank you. And I will see you in part 2 of the presentation. However, I do believe there are 2 more slides, so let's check those out. Okay, so the last 2 slides are simply just revisiting the student learning map to let me know that I'm done with the presentation. And of course, we will do section 3 in the next video, which will wrap up all of chapter 14, and it's going to talk about acid-base reactions. Thank you.